Welcome to lecture 14 of MCS 481. This is the third lecture in chapter 5 in our textbook on making the connection between database queries and geometric data structures. It is lecture 14 and this comes at the end of our 5th week of classes. So this is an important milestone. Next week we will have our first midterm exam. In this course we go rather carefully through the first 10 chapters in the textbook. So we have, at the end of this lecture, we will have done the first 5 chapters. So we are kind of halfway in what we really carefully want to cover in this introduction to computational geometry. So this lecture is kind of not really self-contained regarding, but I will try to make it so. I will start out by sketching the higher dimensional range trees, essentially generalizing the main results that we have covered in 2 dimensions in the previous lectures. In the first lecture, we made a very important assumption that we cannot have equal coordinates, and that's very unrealistic. We will see how we can remove that assumption. And then in the third part, there is an optimization. We can actually reduce the log, the square of the log and the search time to a simple logarithm in a technique that is called fractional cascading, where we are linking sorted arrays. Okay, so we are dealing with multi-level data structures. So here is a schematic of a 2-level data structure. So we have points in the plane, x coordinates and y coordinates. On this plot here, the wedge that is drawn in green represents the tree where the points are sorted on the x-coordinate. So what we did with the KD tree, we were make we had sorted the points on the x-coordinates. We split it vertically, and then we split it horizontally in the next level, and then vertically again. So this is how we build the KD tree. The range tree had an associated tree at every node. So what you see in this picture here in red are the associated trees. So we have a binary search tree on the x-coordinates, where the points are sorted in the x-coordinates, here in green, and in red at every level. So at the root we have a rather big wedge, so this is the entire point set sorted on the y-coordinate. In the same principle, vertical split, horizontal split. At the levels going deeper in the green tree, the associated trees become smaller and smaller. So this is a schematic. I made this picture with Matplotlib. So see here I still have the code available. The picture is over here. So here you can see that I did this with Matplotlib. This is the picture. And you see that the picture is made with the code that is here. I copied this over from the Matplotlib documentation. Took me about an hour to do everything, but this is the result. So in some sense this serves as a very sloppy or intuitive overview of what is a range tree, a tree that we introduced in the previous lecture. Now, what is important is that if we are generalizing this, we split it with lines in 2 dimensions. In 3 dimensions, we're going to split on coordinate planes. So instead of having a line that splits the point set in 2 dimensions in two equal halves, we're going to have one plane perpendicular to the x-axis. So we're going to also split, and again, this plane can be represented by one single coordinate. And we have 3 layers now. Uh, one layer for x, one layer for y. So these are the two vertical planes. And then there is the horizontal plane where we are splitting on the z dimension. So spatial searching is wrapped in Python for 2 and 3 dimensions. So in this course, if we can understand it, visualize it for 3 dimensions, it's enough. This lecture is kind of looking back at the previous 2 lectures. So we defined a range tree in the previous lecture. We gave a 2-dimensional example. Use your random number generator to generate at least 8 points. If you like, you can also take a cube, but that has the problem that there are the same coordinates, so we will come back to the cube later in the second part of this lecture. We have seen a KD tree in the first lecture of this chapter, or in lecture 12, so 2 lectures back. Formulate the 3-dimensional version of this. So the KD tree is the generalization of a balanced binary search tree. Balanced binary search tree typically on 1-dimensional data set, a list of numbers. A KD tree generalizes this to 2 dimensions, and as we have seen in lecture 12, formulate the 3-dimensional version of the building of a KD tree. Exercise 2. In exercise 3, you adjust the 3-dimensional version for the building of a 2-dimensional range tree. And we've actually seen that that code was actually shorter than the for the KD tree. So these are recursive algorithms. Here is the main result for higher dimensions. So we have the sorting that is happening. So we sort for a 1-dimensional tree, and also we sort the numbers for a d-dimensional tree. Now d is a constant, so that is still observed in this big O. So the first term in this recurrence relation is still n log n. If you have dimension 2 or dimension 3, you're doing 3 sorts on the coordinates. Then the time to build it has this log n factor with it, because there we have the cost to building on the associated trees. So these are the depths of these associated trees that we are building. Okay, so this recurrence resolves to n log n when d equals 2. Now we are generalizing this. It resolves to d minus 1 power of the logarithm. And the same recurrence can holds for the storage. So in going from a k dimensional tree for multiple dimensions. Okay, searching this tree. So there's the query time. We use Q for the query time. So we have this recurrence, logarithmic, because that's the height of the tree. Logarithmic also in the second factor in the general recurrence. So if you resolve this recurrence, then you get to d to the power d appears as the power in the logarithm. The next exercise is actually to resolve this recurrence. Um, and that should require some reflection. So perhaps you may do this first for d equals 3, d equals 4, and then you will see that it holds in general. You could also interpret this as you can write also as a programmer, you can see that this is a recursion, which is just a one terms recursion. So you can also substitute things. Um, okay, so by plain substitution, you can solve this. Okay, so this concludes the first part. So let's move to the second part. So just to recap, where did we begin with? So I mentioned database queries. Imagine we have a database that stores data of all employees of a given company, stores their salary, and it also stores their number of children. And we want to know in a range query, so we have two-dimensional query, a salary range, and also a number of children. Now, when we translated this to a geometric problem, so all data points became points in the plane. So here, the salaries is the x dimension, the number of children is the y dimension. So we assumed when we did this transition, we were then focused on the geometry, and the original query actually faded in the background. But of course, you will have find many employees in your database with 2 or 3 children. And it's actually really unrealistic to assume that all points have the same, that no 2 points have the same y coordinate or x coordinate even. So there might also be many people, if you work with fixed salary scales, then there might also be people that have the same salary. Okay, so how can we resolve this? So we will work with composite numbers, and in some sense we have already applied this when we were having points that were at the same height. We did some lexicographical order. How can we do this for points? Well, we have all the points are of course different from each other. So for the coordinates in those points, we replace their points, their numbers for the coordinates. So for if the coordinates, the x coordinate is a, the y coordinate is b, then we make the composite number a slash b. And that's the replacement for the x coordinate, and then the y coordinate is b slash a. Now we have a composite number. How do we compare? One number is less than the other. Well, we first compare the first component of this composite number, and we break ties with the second component, just like we order words in a dictionary. So this is the introduction of composite numbers. So if we have all distinct points in our point set, then all the points will have distinct coordinates. Let's look at an example. So here, if you were to take any simple polygon, you might come up with a triangle or here a cube. square, I'm sorry. So if you take the coordinates of the square, so we see 0 and 1 occurring. So pairs of points have the same coordinates. So you see the replacement of the origin, the replacement of the point 1, 0, and then the point 0, 1, and then the last point 1, 1. So if we list all the x coordinates, then we see that all the x coordinates are different, and then we also see that all the y coordinates are different. At this point, it should also be pointed out that this composite way of thinking is purely imaginary. From a data perspective, one should actually not store anything more, because for any point you have the x and the y coordinate, you can actually work with those coordinates as you work with these composite numbers. No overhead as far as extra storage does. Okay, so now we're doing another arithmetic, another comparison. Now the question is now what happens to our range query. So if we do these range queries now, will we get the same result? So first of all, what is a range query again? So we have this big R here. We have two intervals, x, x prime, y, y prime. In the database query, the x is the salary range, the y is the number of children. So we're going to replace this by a range query on the composite numbers. So we are going to introduce negative infinity and plus infinity for the lower and the upper bounds in the composite numbers of the range query. So with this definition of R hat, so this is the composite version of the range query, we will show that for any point, if the point belongs to the original range, then the composite point, or the point with the composite coordinates, falls within this R hat. Okay, so let's prove it. So for convenience, here is the definition again of this R hat. So we have our lemma. And there is the if and only if. So we start out by translating what P in R means. So spelled out, R is this product of two intervals. It means that the x-coordinate of the point lies in the interval, the y-coordinate lies in the interval. Now let's look at the point with the composite coordinates. Now this has to lie in R hat, so we spell out what is R hat. And then we have the belonging. So we have that the inequalities must happen, but these are then the inequalities on the composite numbers. So how do we compare? Well, we compare the first coordinates. So we are comparing the p-axis. And it's important now, and this fell somehow out of the sky, this minus infinity, this plus infinity. Why did we do this? Well, now comes the reason why. Well, when we have a tie, then actually we always have that the second coordinate lies between negative infinity and plus infinity. Okay, so actually this second part of this composite number in the query range doesn't really matter, and we have the equivalence, and the lemma is proven. Okay, so very well. Now the topic of this lecture is higher dimensions. So what happens now in higher dimensions? How would you apply the composite numbers to a point set in 3 dimensions? So for the numerical example in 2 dimensions, I took the square. In 3 dimensions, you could take the square lying in the plane, but you can be a little bit more ambitious and think about 8 points, the cube. And there you have only zeros and ones, so many points that have the same coordinates. How will you resolve this? Again, all the points are distinct from each other. Um, what we did was in 2 dimensions, we flipped the coordinates. So now actually flipping the coordinates, so we have also composite numbers. You could work with composite numbers that would consists of 3 parts. So this is one permutation of the point. So you have an other representation of composite numbers. There are in the plane with 2 coordinates, there's only one flip. With 3 points, you have 3 factorial, or you have 6 ways how to flip this. So you have to select. You can flip 1 and 2 and 1 and 3, for example, for the x and the y coordinates. Okay, so think about this, how you would do this in higher dimensions. Okay, last topic brings us to the notion of a layered range tree. So the logarithm square in 2 dimensions, it may actually not bother us too much, but still, if we have 1,000,000 points in 10 dimensions, so we have, say, 1,000,000 points, 2 to the power 20, we're going to take that, so 20 is the logarithm, but then we're going to take 20 to the power 9. And that's actually kind of problematic. So, okay, how can we avoid these additional binary searches? So we can avoid this with the use of extra pointers. So this is an extra idea. In some sense, I have still plenty of time in this lecture. I won't fill up even 40 minutes. It will be over in about 8 minutes. So we'll just illustrate the idea. In the textbook, this section is marked with a star. So what is the idea? So let me first again give a numerical example. So we have here 9 points in the plane. You see there are points with the same coordinates. That was my random number generator, but we know how to deal with that now. So if we are sorting these point sets, so in a 2-dimensional KD tree, also in a 2-dimensional range tree, we are left with 2 lists of coordinates that are sorted. So at the top, so going back to the beginning picture, we have our green tree and then the red tree at the root. So in some sense, we have to do a balanced binary search both in the x direction and both in the y direction. And both trees in the x and the y are actually just as deep logarithmic. So this is how we go to the square of the logarithm. How can we resolve this? Well, here is the idea illustrated on this numerical example. So we introduce extra pointers. So if we are looking for, so it's important here that if we are, that, and I should have, it was highlighted in this 2 slides back, we're doing this on the same points. So we have the point with coordinate x coordinate 11. And where does this indeed come from? This comes from 84. So we go then to the y coordinates, and actually we go to the point that is equal or larger than x. So from 11 we go to 38, from 20 we go to 38, from 24 we go to 38, also 29. So you see how we can connect the coordinates of the point that way. In this way we can save binary search, an extra binary search, by linking these two sorted arrays. Okay, that's essentially it. So we reached a milestone in this course. We're closing off chapter 5. There are 5 exercises also. Not all exercises have the same difficulty level. So we have looked into Seagull. The Python bindings support the d-dimensional spatial trees and for 2 and 3 dimensions. So we have actually seen how to do a range query from within Python with a box. So the exercises that are on the slide are essentially meant for you to pause and to reflect back. So in some sense, these are pre-recordings. The fact that I can say this in about less than half an hour means that I didn't pause enough, but during the lecture time there will be ample time to reflect on this. So with that I will stop the pre-recording, and the main suggested activities are to look into Seagull, important for our second project on these geometrical data structures. I will also strongly recommend to look into the textbook.